Welcome back to the Home Lab, and I've got a really interesting little electronics project to share with you today, and something you might want to build yourselves. What we've got here is a binary sunlight duration counter, and what it does is it counts the number of seconds of sunlight in a day and displays them on a binary output. So I've had a lot of fun building this, and it's an interesting little project that combines both digital and analogue electronics. So I hope when I go through it with you, you'll see how the electronics works, and you'll get a better feel for how you can combine analogue sensing elements with digital counting elements. So let's get started and have a look at how I built this. Just before we get started and have a really good look at how I built this and how the electronics works, I just wanted to say a huge thank you again for all of you who watch my little channel, and to PCBWay for constantly encouraging me to make videos and sponsoring the videos I make. As you know, they specialise in printed circuit board manufacture, and whilst I've built this on a breadboard, if you build one, you might want to design yours on a computer and then get them to build the printed circuit board for you. As you know, I like to build my first circuits on breadboard to get them working to begin with, and you might think that's a bit of a waste of time with such a simple circuit as this. But it does allow you to get your mistakes out of the way early on. And something else I find is I often develop and change the circuit. So once I go to the finished circuit board, I'm not having to make massive changes there, and particularly use desoldering techniques, which quite often damage the circuit board. So I want to get it right first on breadboard and then transfer it to the actual finished circuit that I'm going to make. Also, you'll see from the picture that I find it quite useful to use a highlighter pen to trace out the wiring that I've done as I go along, so I don't miss anything. And you know, when you get those annoying interruptions and then you come back to your work and you've forgotten where you got to, this method really helps you pick up from where you left off. You'll see that I've used 16 LEDs here to represent the number of seconds of sunlight experienced during the day in binary form. One of the 74590 counter ICs can only produce an 8-bit number, with the 8 LEDs showing 11111111, and so that would only equate to 255 seconds in decimal, or about 4¼ hours, which even in the UK is not quite long enough. So I added a second counter chip that receives a carry signal from the first, enabling another 8 bits to be displayed, which gives a 16-bit binary number, and that equates to 65,535 seconds in decimal, which is about 18.2 hours, which is more than enough to display the number of seconds of sunlight in a day. Now, obviously, I need to calibrate the LDR circuit to define what is actually meant by sunlight and dark, so the thing switches on and off at the right times. But just setting it up as I had, here's an example from the 7th of August 2024, and it was taken at 9 PM when it stopped counting, and you can see we got 1011, 0110111111, I think, if I've got that right, which is 46,847 seconds in decimal, which is about 13 hours of sunlight. And it's interesting, when I looked it up online for that day, it gave the sun rising at 5:41 AM and going down at 8:49 PM, which is 15 hours. So my 13 hours compares reasonably well to the 15 hours of sunlight we had, but perhaps I need to make the LDR circuit just a little bit more sensitive if it's going to agree with what it says online. I started my breadboard build by utilising the 555 timer circuit bits off a breadboarded light chaser circuit I was building to save me putting together another one at this stage. I could of course have used a signal generator instead. Initially it didn't work at all, and I spent ages trying to see what I'd done wrong. Turned out that some of the old breadboard connections were not clean, resulting in intermittent connections. Never a good thing with digital pulse driven circuits. With this sorted, in the end it worked, though I didn't test all of the 16 LED outputs. The LED that you can see on the far right here is actually the 7th bit. I did test to see if this bit lit up after 2¼ hours, which would mean that both chips were working and the carry function worked correctly as well. With this all done, it was time to pull it all apart again and rebuild it onto a soldered circuit board. After installing the IC sockets, I started with the 555 timer end, and once that was all wired up, I tested that before moving on to the wiring of the 74590 binary counters. As ever with me, the 555 part appeared not to be working at all, and on investigation it was the wiring of the LED indicator switch that was at fault. I put that LED in to show if the 555 timer was actually working. So yet another lesson in don't always believe your test gear. With the main circuit board built, I then tested the working of the first 8 bits by connecting up some yellow 5mm LEDs. This also allowed me to test the operation of the counter reset and counter hold buttons. I still needed to deal with why the LEDs were blinking a bit when on and not staying properly illuminated. In my haste to see it all working, it turned out I'd forgotten to ground both pin 14s on the counter chips, which are the output enable pins. I'm surprised it worked at all, but this is a salutary lesson in the fact that if you don't keep digital chip pins at the right potentials, the results you can get can be far from predictable, and often they're very erratic indeed. With most of the circuit built, I then wired up all the 16 LEDs and left it running to test the carry function fully, and this worked really well. I then needed to calibrate the 555 timer to produce pulses every second. Currently it was sort of running just a little bit fast.
6, 7, 8, 9, 10.
I therefore adjusted the value of one of the resistors on the 555 timer's resistor network, and I used a few resistors soldered together to get the value that I actually needed. And I got it pretty close to 1 Hertz, and I then tested it over a number of pulses with a stopwatch to see how accurately it was counting. Finally, I needed a way of making sure that it only counted when there was sunlight, and I thought about this for ages and ages and wondered whether I could get a solar cell to actually drive the counters and a rechargeable battery to hold the count when it was dark. But in the end, the solution was quite simple. I was just bridged the count hold switch and resistor with a light dependent resistor and adjustment potentiometer to set the light level that triggered the circuit to start counting, acting as if someone had released the counter hold switch. Mounting that on a separate little small circuit board, this worked beautifully, showing that the simplest solution is often the best. I had great fun picking a nice sunny colour of perspex to mount all the electronics upon. With the template marked out, I drilled out all of the holes with varying sizes for the PCB mounts and the LEDs, etc., and the bundles of wire that had to go through to the back of the board. It was then quite a quick job to bend the end of the sheet to create a stand. Not an easy thing to do with the camera and the tripod in the way. And would you believe it, I also forgot that I had a heat gun in the workshop. I therefore made a bit of a mess of this, but with a bit of later reheating and adjustment, I think you'll agree it's come out okay. Then to my favourite bit, the great reveal, as you peel back the protective cover on the perspex sheet. Finally, it was time to mount all of the electronics onto the perspex sheet, starting with the circuit board on some nice brass hex standoff pillars. Thankfully, I drilled the holes in the right places and in the right size to pass the wiring through as well. This I did as neatly as I could, and then pushed the indicator LEDs into their correct position in the sequence. I had to make sure I got them in the right order there. I left the separate small LDR circuit board loose but on stiff wires at the back, so this meant it could be bent into any position that was needed to catch the light correctly. The whole device uses only about 150 milliamps of current, so I used an old 8 volt mains power supply to power it. You could use a PP3 9 volt battery if you wished. The finishing touches were added in the form of some labels printed on my fantastic Brother label printer, which I use all of the time. And then it was time to put the whole thing in the window to happily count away, sunlight allowing. Here you can see it working and how it counts up a second at a time. Once the first chip has done its job and counted up to 255 seconds, you can see the carry onto the second chip to continue the count at 256 seconds, about 4 hours and then beyond, all the way up to 65,535 seconds, or about 8 hours. So let's have a quick look at the circuit diagram of the circuit that I built, and it's really not that difficult. It consists of three main parts. So on the left hand side here, a circuit that produces pulses every second, a circuit here that counts the number of pulses it's received, and then a circuit here that works out whether this circuit should count. In other words, is it light or dark? So let's start with a pulse generation, and you'll see here I've got a typical 555 timer circuit. You'll recognise the capacitor and resistor networks here that make sure that this counts at the right frequency. I've written high tolerance resistors here. They don't need to be, but this one here was actually made out of 3 high tolerance resistors that I soldered together in series to get exactly the value I needed to make sure that this counted as close as I could to seconds. Let's now look at the circuit that does the counting and displaying. So I've got the positive rail up here and the negative or 0 ground down here. I put 6 volts, but this will quite happily run at least at 10 volts. I've got it running at 8 on the one that I built. So the pulses come out of the 555 timer, and here's an LED between the pulse output, a current limiting resistor and ground. So this LED, which is the green one on my circuit, flashes just to show me that the 555 timer is working properly. It then feeds into the clock input of the first 74590 chip, and this is a binary counting chip. So every time it receives a pulse, it counts up 1 in binary, and it can get to 255, and then that's all 8 bits switched on. So we then come out of that, we come out of the carry and into the clock of a second 74590 chip, and that carries on counting to give the more significant bits. So I've shown here the first bit, the first one that would light up, and this pin 15 becomes high or 5 volts, and that means a current can pass through this LED, through a current limiting resistor and down to ground, lighting that LED. And obviously there's another 15 LEDs all the way along here to show the whole 16-bit number. A couple of other bits to look at. If you want to reset this without actually switching it off, there are pins here, pin 10, which are counter reset pins. And if you look at the moment, we're connected to high here through a pull-up resistor. So this point is actually at 6 volts because it's not connected down to ground. So at the moment, it's not resetting. But if pins 10 on both chips are turned to the low state, to 0, in other words, we switch this switch here momentarily, then the counter will reset. There's also a second connection we need to know about, which is this one here, pin 14. And I think I got this wrong when I first started building it. You've got to make sure that that is held down to 0. And if it's held at 0, it enables these chips to count. It's a bit of a weird thing. You kind of make sure that pins 14 are connected to 0 volts, and that kind of switches it on to count. So with that in mind, how do we get it to count only when it's light? And there's a clever little circuit here, and this is an analog, not a digital bit. We've got a wire going here to pin 12 on both chips, and that's the count enable. And again, it's rather counterintuitive that if the count enable is low, in other words, it's connected to 0, the thing counts quite happily. And if the count enable is high, it stops counting. So I've got a switch here that I can switch to high, and that will make this point high and it will stop it counting, and that's momentary press switch. So that will mean that we can just pause the count. But something else I've done. Here you'll see, finally at the end, there's a light dependent resistor which resistance goes down when light hits it, and a variable resistor or little potentiometer here. Now the way this circuit works is that if there's light on this light dependent resistor, its resistance will be very low. So basically it behaves like a wire, and that will mean that point is low, and therefore the chips will count. So sunlight on the light dependent resistor, I'm sounding like I'm teaching my A-level and GCSE students here. The resistance goes down, the voltage here goes lower, and if it's low enough, it'll switch on these chips and start them counting. However, if it gets dark, the resistance of the LDR will go up, and if it becomes high enough, this point here, depending on the position of this potentiometer, will become high, and if it becomes high enough, we'll get a positive voltage on both pin 12s, and that stops the chips from counting. It pauses them. So if we got sunlight again, they would start counting again. The final bit is, when must that happen? Well, it's a balance between the resistances of these two, and you can adjust this little potentiometer or variable resistor here so that you set the level that sunlight will cause this thing to switch on and off. Whether you want it to be very bright and start counting, or very dim and start counting. So I hope you've got a good understanding of how the circuit works now. I always think these things look really complicated until you break them down into chunks. And obviously here you'd be learning a few different bits of electronics that are brought together. The pulse making circuit, the digital counting circuit, and finally the analog sensing part, and bring them all together to make some circuit that has a particular use. So I do hope you enjoyed that video and this little build project. It's been really fun to do, and whilst you might say what a useless item, it does serve the purpose of teaching you quite a bit about digital and analog electronics and how they connect together, interact with each other. And I think it just looks quite pretty on the windowsill. Certainly the family's been somewhat interested in what I've been up to. Anyway, as ever, thanks very much for watching, and do stay right to the end of the video, because after I've finished speaking, I often put in a few extra sequences that I didn't include in the main film, and right at the end there's some links to some other videos that might interest you. Anyway, I'll be making another video soon, and do join me then.